So, what I have is I am going to describe two methods of constraint optimization. So, constraint optimization, and we will describe the method via the Hamilton constraint optimization, fine. Okay. So, the first method is the penalty function method. The first method that I have is the penalty function method. Okay. So, what exactly is this? We will see that we are going to change the inequality into an equality constraint by introducing the so called penalty function, or in the language of calculus of variation introducing a non holonomic constraint or a differential constraint. Okay. So, what we have is, consider this system, consider the system given by x dot bar, which is f of x bar u bar t, and I am given also the performance index, which is given by j integral of t 0 to t f of v of x bar u bar comma t dt, and where my x and t are my usual state and control variables. So, x bar and u bar are my state and control variables, and now we look at some inequality constraints. So, consider inequality let us say vector constraints. We will look at set of constraints. So, vector constraints, let us say on state variables. So, g bar of x bar comma t is greater than equal to 0, right. So, inequality vector constraints. So, let us to deal with these vector constraints, I am going to introduce a new state variable, let us say x n plus 1. Okay. So, the idea is so these are my constraint optimization problems. These are my problems. These are few more methods. So, we have done one method earlier. So, these are my other methods as well. So, I am just mentioning two more methods in this setup. So, the idea of this penalty method is as follows. We are going to introduce a new state variable. We will introduce a new state variable as follows: my x n plus 1 by x n plus 1 dot is equal to f n plus 1 of x bar comma t as follows. So, this is also, this right hand side is written as follows. So, this is g 1 times x. So, the constraint g 1 that we had, we take a square times h of g 1, where h is a Heaviside function. Let me write down this expression and it will clear very soon, and so on, plus g p of x bar comma t square times h of g p. So, suppose we have p inequality constraint condition, and where my h of g I are my Heaviside function. So, h of, so where my h of g I is my unit Heaviside function. Okay. So, this is also equal to either 0 or 1, right, and the 0 condition is if my constraint g of x I, my constraint is Heaviside function, if g I of x bar comma t is greater than equal to 0, and if this g I of x bar comma t is less than 0, then I have the following this equal to 1. Notice that when my constraint is negative, we are taking a square of the constraint. So, this will always be positive, right. So, which means that my right hand side will never be less than 0. So, we will have the minimal value of the right hand side will be 0, right. So, with that further we need boundary conditions for this new variable. So, further require the boundary condition to vanish for the new variable, require that the new variable has the boundary condition x n plus 1 at t naught is equal to x n plus 1 at t f is equal to 0, right. So, now we set up the Hamiltonian. So, set up my Hamiltonian. So, h of x bar, u bar, lambda bar. Now, lambda is the Lagrange multiplier for n variable system. We also introduce a second Lagrange multiplier, which is for the n plus 1th variable and then t. Okay, so, this is also equal to v of x bar, u bar comma t. So, these are all n dimensional vector functions plus lambda bar of t times f of x bar, u bar comma t. So, this is the usual Hamiltonian setup, but there is an extra term plus lambda n plus 1 f n plus 1. So, that is the added term in the Hamiltonian with the constraint, right. And then we now apply our Hamilton's equation. So, apply optimality condition or Hamilton's equation. We see that we have to solve the following set of equations: x bar dot star is equal to partial h partial lambda, right, h bar star dot, this is the start condition, and we see that partial h partial lambda will be f. So, f at x star comma u star comma t. So, this is my optimal condition for the state variables. And then of course, we have an extra state variable x n plus 1 that we introduce. So, we need an extra equation. So, x n plus 1 dot star will be partial h partial lambda n plus 1, and this is equal to f n plus 1 at x bar star comma t, right. Okay. And then for my co-state variable, we also have n plus 1 equations. So, this is my state variables, and my co-state variables, are lambda bar dot star is minus h minus x, and then the extra condition that we have is lambda dot star at n plus 1 is equal to minus h minus x n plus 1, right. So, these are my co-state variables. So, we have 2 n plus 2 equations to be solved, right. Notice that the only dependence of h on x n plus 1 is via lambda n plus 1, right. So, h does not explicitly contain x n plus 1 as such. Okay. So, let me just highlight this penalty function method with an example, right. So, let us look at an example. So, this is example number what have we got here, example number 3. So, example number 3, the example is consider the system, this is a second order system, and the system is given by x 1 dot is equal to x 2 and x 2 dot is equal to u. So, this is a similar system that we had solved in our previous example, and this time my performance index g of u comma x comma u, right. So, how did we really represent j? We represented in the form of j, right. So, well we say j, fine. Okay. So, j of x bar comma u, this is half, this is given to be half from T 0 to T f of u square, well this is x 1 square plus u square and dt, right. And further it is given that the final point T f is free and the final state x of T f is also free, and the control u t is constrained. Further I am given some constraint, the control function u t is constrained as u from minus 1 to plus 1, right, and this is for all t from T 0 to T f. Okay. And further I am also given that x 2 is constrained, the state variable x 2 is constrained, right. Okay. Is given by the following constraint. So, x 2, the absolute value of x 2 is bounded above by 3, right, for all t in our interval under consideration, right. Okay. For all t s, this is all under closed interval. Okay. So, so now what we have is this absolute value can be changed into two inequality constraints. Notice that my state constraints are as follows. My state constraints are as follows. I have x 2 plus 3. So, x 2 plus 3 must be greater than equal to 0. So, let me call this constraint as G 1 greater than equal to 0, and my constraint 3 minus x 2 is greater than equal to 0. So, call it G 2 which is greater than equal to 0, right. So, my state constraints are as follows, and then I set up my Hamiltonian. Okay. So, these are essentially my constraint problems where we are putting constraint on the state variables, right. In my previous discussion where we were discussing the Pontryagin minimum principle, we were putting constraint on the control variable. So, that methodology remains as long as we are putting constraint on control variables. So, so let me just slightly mention the constraint optimization is what we are doing is the constraint on the state variables. Okay. The control variable you follows the same as my Pontryagin minimum principle, fine. Okay. So, we set up the Hamiltonian. The Hamiltonian this time will be H is going to be well V plus lambda. So, let me write down the complete Hamiltonian. So, this is going to be V plus lambda times f times lambda n plus 1 times f n plus 1. So, let me write it down. So, that is my step 1. Okay. So, my Hamiltonian is x 1 square by 2 plus u square by 2. So, that is my V, and then plus lambda 1 plus lambda 1 x 2 plus lambda 2 u, that is my lambda times f, in fact it is a dot product, and plus I have the last variable plus lambda 3. So, lambda n plus 1 times f n plus 1. The way f n plus 1 is set up is using my Heaviside function. using the two constraints I have. So, g 1 square is x 2 plus 3 whole square times the Heaviside function of x 2 plus 3 and plus 3 minus x 2 whole square times the Heaviside function 3 minus x 2, and then well, so that is it. So, this is my Hamiltonian, and then I have to set up the equations for my state variables and co-state variables. So, we will have 2 n plus 2 equations. So, let us do that. So, step 2 is x 1 star dot, well, that has to be partial h partial x 1 partial lambda 1, that will give me x 2, and x 2 star dot will be with respect to lambda 1, and that will lambda 2, and that will give me u, right. And then my x 3 star dot will be again with respect to lambda 3, I am going to get the f n plus 1. So, this becomes f n plus 1, which is x 2 plus 3 whole square, the Heaviside function x 2 plus 3 plus 3 minus x 2 square, the Heaviside function 3 minus x 2. Okay. And then my other co-state variables are lambda 1 dot star is equal to minus h partial x 1. This is lambda 1 dot star is minus x 1 star. So, we are just differentiating. So, lambda 2 dot star will be minus del h del x 2, and we see if we are to differentiate with respect to x 2 appears as lambda 1. So, we get minus lambda 1, and then we will have a huge expression minus 2 times lambda 3 times the derivative of f n plus 1 with respect to x 2. So, I leave it here, let the students complete this expression, and also lambda 3 dot star is minus del h del x 3, which is also equal to, so h, let us see, h does not have a variable x 3. So, this will be 0, right. So, which means that immediately I see that lambda 3 is a constant, lambda 3 is a constant. Okay. So, what have we got? So, then I have to solve these 2 n plus 2 equations, and I have constraints 2 n plus 2 constraints x 1 to x 3 and lambda 1 to lambda 3. This is should be solvable. The next step is from here I find my optimal control u star. So, to find the optimal control u star, so let me see the steps here. Okay. So, to find the optimal control u star, let us look at the Hamiltonian again. Notice that in the Hamiltonian u appears here as a, well, this u square by 2, and this is what have we deleted here. So, this is lambda, so this is v, yeah. So, u appears here as I have circled, and u also appears here. So, which means that if we were to minimize or maximize the Hamiltonian with respect to this function u, we only need to look at the circled quantity, right. So, let us look at only the circled quantity and minimize the Hamiltonian. To find u star, consider the modified Hamiltonian h u, which is u square by 2 plus lambda 2 times u. These are the only two terms which contains my variable u, and from here when I take the derivative of h u with respect to u, I see that this is u plus lambda 2 is equal to 0, or from here I see that u is equal to minus lambda 2, right. Okay. And then well, of course, we have another constraint that we have so far not considered, and that is the constraint on the control variable itself, that u cannot be bounded, u is bounded above by 1, right. So, that has to be also included. So, note that since u of t is bounded above by 1, u of t is bounded above by 1, I see that my constraint variable u star of t is plus 1 if notice that u is minus lambda 2. So, if lambda 2 attains the minimum value or lambda 2 attains the left boundary value, then u attains the maximum value which is plus 1. Otherwise, if lambda 2 is strictly between minus 1 and 1, then u star is nothing but minus lambda 2 star. Otherwise, if lambda 2 is greater than 1, then u is minus 1, right. Okay, u star is minus 1, fine. Okay. So, what have we got? So that is how. So all I have to do now is, well, we have 6 variables, 6 unknowns, 6 equations. The unknowns are x 1, x 2, x 3 and lambda 1, lambda 2, lambda 3, and from there when we plug, our u is minus lambda 2 provided it is not on the boundary, right. So, the control is found right away from our solution. So I would just end the discussion in this example by saying that xi's and ui's, well, xi's and lambda i's are found from step 2, right. Xi's and lambda i's are found from step 2, and that should be the end of the discussion in this example. Okay. So, that highlights our penalty function method, where the penalty is placed on the state variable. Okay. We are now going to wrap up our discussion by highlighting yet another method, the final method, namely the slack variable method, the slack variable method. So, what exactly is this method? Also known as the Valentine's method, right. So, I am going to discuss this Valentine's method. So, we introduce a slack variable to change our state inequality into an equality. So, that is the whole idea of this slack variable method. So, introduce a slack variable to change the state inequality, constraint, state the inequality constraint into an equality constraint. Okay. So, now we are going to consider again let us consider the statement of the problem, and within the problem we will introduce our inequality constraint, right. So, consider the optimal control system, the system given by x bar dot is equal to f of x bar u comma t, and I am given that x at t 0 is x 0. Let me call this setup as 1, my plant condition, which minimizes our performance index j, which is f of x of T f comma T f. This is typically going to be our cost function, plus an integral term from T 0 to T f v of x bar comma u bar comma t dt, right. So, this is minimizing the performance index subject to the state variable inequality given by s of x bar comma t is less than equal to 0. So, that is subject to this inequality, right. So, I am now switching my notation where my cost function is denoted by f. So, this is my cost function in the Bolzá problem that we discussed earlier, and my notation S is the state inequality constraint, right. So, now I am going to change this inequality constraint into an equality constraint by introducing a new variable known as the slack variable. So, introduce the so called slack variable alpha such that now S of x comma t plus alpha square, let us say typically a function of the independent variable t by 2 is equal to 0. Notice that alpha is real valued, it is a real valued function, and the square of alpha will always be positive, which means S is negative alpha square by 2 or S is less than 0 and equal to 0 only when alpha is 0. So, certainly this new equality certainly satisfies the original inequality with this new variable, right. So, well, the assumption here is that S is differentiable up to some orders. Let us say the constraint is differentiable up to p orders. So, from here I can get p different constraints. So, what is the idea of changing one equation into p equation is sometimes the function alpha of t is not solvable. So, rather than solving this equality, we directly change this equality into set of simpler equations in which the final equation is such that alpha can be explicitly expressed in terms of other variables, right. So, what did I say? So, let me call this this condition, let me call this as 1 prime and this as 1. So, what I have said is S is the pth order, S is the pth order constraint, S is the pth order constraint, and such that pth order constraint such that the pth order contains u of t explicitly. Okay. The pth order contains u of t explicitly. Okay. So, then what shall we do? Again, since it is a pth order constraint means that S is smoothly differentiable up to order p. So, we exactly do that. So, differentiating 1 p times p times with respect to my independent variable t, right, and I am going to get the following set of relations: S1 of x comma t plus alpha 1 is equal to 0, and then S2 of x comma t plus alpha, well, we differentiate this alpha 1 square plus alpha 2 is equal to 0 and so on, right. And finally, we will have SP plus terms involving alpha 1 alpha p, right, set equal to 0. So, what have we got? We see let me call this set of equations as 2, and in 2, well, the pth equation is such that I can explicitly write my unknown function alpha in terms of SP and other variables involved, and then we back substitute the other variables from the previous set of equations, okay, given by 2. So, what have we got is, so let me just say, so where my SI is the regular derivative del S del I, well, d I ds, the ith derivative, and my alpha I is the regular derivative d I alpha by d t I, and what else? So, my pth equation, the pth equation that I just derived gives me u, the control variable, explicitly as a function of all the other quantities that I have, alpha to alpha p, right. So, this is from my pth equation, let me call this as condition number 3, right. So, that is how we find the control from the pth equation. So, we have to differentiate p times. So, which means our our modified plant condition or modified equation 1 prime, modified 1 prime, originally it was is now x bar dot is f of x bar comma u now is g of x bar comma alpha p comma t, and I am given that x at t equal to t 0 is x 0, and further I have that alpha dot is equal to alpha 1 and alpha 1 dot is equal to alpha 2 and alpha p minus 1 dot is equal to alpha p, right. So, these are my notations, and notice that so these are my new set of state conditions or sorry plant conditions, where now I have introduced certain new variables, right, alpha 1 alpha 2 to alpha p minus 1, and with the following initial condition alpha at t equal to t 0 is alpha t 0 and alpha 1 at t equal to t 0 is alpha 1 at t 0 and so on, alpha p minus 1 at t equal to t 0 is alpha p minus 1 at t 0, right. Okay. So, finally, my modified performance index is seen to be as follows. So, J now is f of x of T f comma T f x bar of T f comma T f integral from T 0 to T f v of x bar comma g x bar comma alpha p of t, right, dt, and then well from here. So, this is my modified performance index, and finally, my modified initial condition, I need to find all these, this is still, these are still unknowns, right. These values here that I have just mentioned, that can be actually found from our set of p equations given by 2, right. So, from here I can find the initial values to all the alpha i's. So, modified initial condition from my set of equations 2 are as follows. So, alpha at t 0 is square root of negative 2 s at x of t 0 by t 0, and alpha 1 at t 0 is minus s 1 at x at t 0 divided by alpha at t 0 and so on. We can find all the values, this is from 2 itself, right. So, we are ready to state all the equations. We have how many equations have we mentioned? Well, I call this as 4 and I call this, I have 3 as well, 3, 2 and 1 primes. Okay. So, all my relations from 1 prime to 3 and 4, they said they are going to describe my unconstrained problem for the control variable u or alpha p, whatever it is, because the pth equation will be given alpha p and that will directly give me the relation that will directly give me the function u, right. Okay. And we could apply we could apply the Pontryagin minimum principle if we have, if there is a constraint, if there is a constraint on, if there is a constraint on u, right, we could always do that. So, quickly let me just summarize how we set up the problem. So, now we have slightly more equations to solve. So, define, so we are going to define instead of n vectors, but not n but n plus p vectors. So, n plus p state vectors, define n plus p state vectors as z of t is equal to x bar of t, alpha of t, comma alpha p minus 1 of t, right. Okay, we define our new plant condition. So, these are my vectors. So, this is n dimensional vector and we have p dimensional vectors, right. So, I am rewriting the entire problem in an n plus p dimensional state vector formulation. So, my new plant condition is z dot is equal to f of z of t, comma alpha p of t, comma t. Notice that I am very conveniently replacing my control function with alpha p, because the pth equation will yield my control, where f is an n plus p dimensional vector. It is an n plus p dimensional vector representing the RHS of my condition 4, right. So, we had all the equations that we had described, and finally, I define my Hamiltonian. I define my Hamiltonian, which is again the same, h is equal to v plus lambda f, where my lambda is n plus p dimensional Lagrange multiplier, n plus p dimensional Lagrange multiplier. And finally, let me complete this description by writing down the equations to solve. I have my state vector equations, state variables in the form of a vector equation. My state variables are z dot of t will be partial h partial lambda bar, right. So, that is how my state variables are, and then of course, with given bound initial condition, I need the initial conditions as well, and of course, my co-state equations are as follows: lambda bar dot, this is z bar dot. So, lambda bar dot t is minus h z, right, where now I have that lambda of T f is f x comma 0,0. So, my f x is an n d problem, and this is my so notice that only the first n components of lambda will be non-zero, the rest are all set equal to 0, the p values, right. And finally, my control variable is given by del h del alpha p, right. So, differentiating h with respect to alpha p or h alpha p, I know that h is not a function of alpha p. So, that will be 0, and from here I can get my control solution u star. Okay. So, that completes the description of our slack variable method, which completely converts the inequality into an equality and then converts our original system into a slightly lengthier system, but system which can be treated as an unconstrained optimization problem. So, all these so in this lecture I am going to end my discussion on the optimal control theory and mention that students are requested to look at the text I have highlighted in my introductory video on the reference for more problems. and in the next lecture I am going to start with another application of calculus of variation, namely looking at the motion of carbon nanorods. So, thank you very much for listening.